Hi guys, just give me a second. I am about to share my screen now. So my topic for project one of ECEC 572 is neuron modeling in hardware. My name is Paris Doshi, and I hope you guys enjoy this presentation. I'm going to start off by introducing you guys to both biological and artificial neurons. From here, you'll realize the inspiration for the designs of these neurons and of these artificial neurons and how they work exactly. So I'm just going to stop sharing my video feed now with you and just let you focus on the presentation. So then, after introducing these neurons, I'm going to um, get into the FPGA implementation of these neurons as they are most common. After that, I'll be examining FPAA implementations of the neuron model. And finally, I will be looking at neuron modeling in ASIC models. So first thing we're going to do is have a look at what are neurons, and that there are two major classes of neurons, both biological and artificial. So the biological neurons are the basic building blocks of the human brain, and they're responsible for sending, transforming, and receiving signals. The human brain has roughly 100 billion neurons and 100 trillion synapses, which connect these neurons to each other. So it is believed that the immense computing power of the brain is a result of these parallel interconnected nature of these neurons. So if you look up here, this is a single neuron, and the brain would possibly have 100 billion of these working in with all these working in parallel. So next, I'm going to describe the structure of the neuron. So I'm only going to be defining some of these attributes because I'll be focusing on what's relevant to our artificial neuron structure as well. So I'm going to start off with dendrites. Dendrites are these like branch-like structures right here. These dendrites receive messages from other neurons and allow the transmission of these messages to the cell body we have right here. This cell body then uh, performs upon these information received from the dendrite and sends them to the through the axon. The axon is this tube-like structure which carries electrical impulse from the cell body and to its axon terminals. From these axon terminals, the synapses take the information and pass them on to the dendrites of other neurons. And this is how neurons can sort of connect with each other and work along with each other. So, so let's talk about an artificial neuron now and how those work. So here we have an example of a sample artificial neuron, which takes four inputs labeled X0 to X3. These neurons each have their own weights, W0 to W3, and they're multiplied with their own respective weights and sent through a summation function, which takes in the sum of all these inputs and their weights, and then applies them to and sends them to an activation function, which makes a decision Y based on these sum of the input and the function itself. So a mathematical model of this is shown right here, where A equals the sum of all the inputs and their weights, and Y equals K plus T is the activation function applied to the input sum. So you must be wondering, what are weights? Well, weights are help us place the importance of different neurons, so they can be multiplied with the different neuron inputs, and they can uh, uh, make decisions based more heavily on some neurons inputs, and for example, based on more heavily on X0 and less heavily on X3 if the weight on X0 is higher than X3. This is referring to my previous example in the previous slide. And then we look at activation functions. Well, activation functions come in many different forms, but basically they help determine the output from the sum of our inputs. We can have We can have linear activation functions, such as step responses, or we can have non-linear activation functions like sigmoids. We also can place biases on these neurons to favor possibly like a 1 over a 0 or something like that. And these neurons connect with each other to sort of interconnect to form a neural network. A small representation of this shown is shown right here in this diagram. And if you think about it this way, a neural network is sort of a crude representation of the human brain. So now I'm gonna compare the biological neuron to the artificial neuron, so you can actually see how the artificial neuron was completely inspired from the biological neuron. So the dendrites here represent the input connections. So here, all these orange squares are related to the dendrites here. And then the cell body sort of acts like a summing activation function that takes these inputs from the dendrites and sums all of them here. So this activation function is just like the cell body. Sorry, so the summing and the activation functions are just like the cell body. And then the axon that sends it to the output is sort of like an axon, which leads to the output connections of our model right here. And then synapses are just wires that connect different one neuron to the next. So now we will discuss how to implement neurons in hardware. So let's assume we have the same neuron as we had in the previous example that takes 4 inputs. Now we need to decide what hardware to implement this in. First of all, we will not be implementing these in microprocessors, primarily because custom circuits built on FPGAs, FPAAs, and ASICs perform significantly better than these microprocessors. Uh, so right here, um, right here, I am going to describe the data path of a standard neuron model. So here we have all the gates and all the diagrams here. So um, this image basically represents a circuit diagram for that neuron. So again, if you look at this image, we've got 4 inputs and 4 weights. In this circuit diagram, we've got 4 inputs and 4 weights here. The weights are actually stored inside registers for now. But what ends up happening is, as we get each input, it's sent to the mux, and the weights are also taken in from the mux, and they're passed to the multiplier, which multiplies the uh, input value, like x0, and the weight corresponding to x0. And then these multiplied numbers, which would be 16 bits if our input is 8-bit input, then our then this result gets sent to the adder, which that accumulates all these x0 to x3 uh, input multiplications with their weights. So it has the cumulative sum so far. So once we have added the two numbers together, they get stored again inside the accumulator, which gets the signal load accumulator from the control logic. And then after that, again, this output of this accumulator is again wired to the adder, and the cumulative sum is taken. After that, uh, once the complete sum of all 4 inputs have been taken, it is sent to the activation function, which will make a decision based on the values of these inputs. As we mentioned earlier, we can have linear activation functions, nonlinear activation functions, and the output decision is sent. So next, we're going to actually discuss neuron. We're going to actually discuss modeling neurons in FPGAs. So first thing I want to talk about is the McCulloch-Pitts neuron. This was developed by Warren McCulloch, who's a neuroscientist, and Walter Pitts, who's a logician in 1943. And they published this in a paper called the logical calculus of immanent in logical calculus of the ideas immanent in nervous activity. This neuron model actually didn't even have any input weights that we mentioned earlier. It was simply binary inputs or single bit inputs and a single bit output. This image here is by Akshay L. Chandra. And yeah. So Banyulis and his team implemented this neuron on a Xilinx XC4000 series of an FPGA back in 2003. So what they were doing here, is that they were trying to test the three different activation functions and their impact on an FPGA to see how much of a workload impact it or performance impact it has on an FPGA. So the three activation functions considered here were the step, ramp, and the sigmoidal activation function. The step and ramp are both linear activation functions. The sigmoidal is a non-linear activation function that actually relies on exponentials and is quite complicated. So a step and ramp function, you can imagine how they would appear on a graph, but a sigmoidal looks sort of right like here. I've added an image of a MATLAB plot of a sigmoidal activation function. So what we realize is that when we implement a step function, we only use 5 out of the 196 control logic blocks, and we only use 2% of the total chip utilization, and the maximum delay is 5.15 nanoseconds, and the working frequency is really high of 194 megahertz. But now when we look at ramp functions, we use a little more control logic blocks, a little more functionality. We go from 2% to 5%. There's not a significant increase in delay. It's still workable. And the frequency goes down by 60 megahertz, but that's not as significant as when you transition to sigmoidal activation functions, where we use 78 out of the 196 control logic blocks, which is 40% of the chip utilization. So the maximum delay between the pins actually goes 3 times. There's actually 3 times increase in the maximum delay between the pins, and we can see that the maximum working frequency goes all the way down to 60 megahertz. So here we can clearly see the effect that the choice of an activation function has on hardware. So if we were implementing many neurons in parallel, then we would have to seriously consider what type of activation function we want to use and the accuracy of these activation functions. So next I'm going to move on to neuron implementations in FPAA. So first we will go over the Hodgkin and Huxley neuron model, which is the most famous neuron model out there. And then we will move on to the Fitzhugh and Nagamo model. So Alan Hodgkin and Andrew Huxley developed this model in 1952. They were investigating the initiation and propagation of action potentials on the giant squid axon. So one thing you guys should note here is that, sorry, I meant squid giant. So squid giant axon, not the giant squid axon, because these are two different things. The squid giant axon is a giant axon inside the squid, whereas a giant squid axon is an axon belonging to a giant squid. So it's very important to make that distinction here. So what Hodgkin and Huxley did was they performed a voltage clamp experiments where a step voltage was given and was applied to a squid giant axon, and current measurements were taken from the ion channel, and this data kind of helped them derive the equations for the dynamics of their model. And this model is represented right here. As you can see, it's four orders. Sorry, there are four ordinary differential equations here. And this and so yeah, till this date, this model is actually considered one of the most accurate and is often used as the reference model when developing new neuron models. So now I'm going to talk about the implementation of Hodgkin and Huxley neuron in an FPAA. So first, we're going to actually talk about FPAAs briefly, because compared to digital circuits, analog circuits can perform complex nonlinear operations with significantly less transistors, while digital circuits require hundreds or even thousands of transistors to perform these same operations. Uh, then I will. Then I'm going to talk about yeah, and the analog computation here also performs these operations in FPAAs with far less power and power per computation than digital circuits. So on the right here, we have the diagram of the XCOS model implemented of XCOS model implementation of the Hodgkin and Huxley model. We can see that there's the Hodgkin Huxley neuron model here. Unfortunately, we couldn't get circuit level diagrams as this research did not share this. We can also see here that there's a ramp generator. The floating gate switches are actually acting as synapses here, and what's um, and here we can also see the spiking behavior of these Hodgkin-Huxley neurons. This is a very famous characteristic, their spiking behavior. And what's interesting about this implementation is that it uses 0.79 microwatts of power. Yeah. So moving on to next slide. Next thing I'm going to talk about is the Fitzhugh-Nagamo neuron model. So the Fitzhugh-Nagamo model is also implemented in the FPAA here. And here, part A here in this equation here shows the multiplier blocks for the x cubed being calculated here. So x comes in, it gets multiplied with itself twice to get you x cubed. And then this part B of this diagram here, of this logic block, in a way, here shows the differential, shows the differential equation of y. So this differential equation right here. And this is created using a 3-input sum-inf block. And this is also connected to, this is actually just connected back to itself also here. And in part C here, we are implementing the dx over dt characteristic here, where which is basically the differential equation for x. And here we have a 3-input sum-inf block, which is connected to gain-inf block, and we also have a sum integrator here. So yeah, so that's basically the circuit level calculations of the Fitzhugh-Nagamo neuron model here, right here. And this was actually implemented on an AN231 board. And since there are only 4 control access blocks per chip on each of these boards, this research actually decided to chain 2 boards together. I thought this was very cool implementation of FPAAs, as we don't usually see a lot of chaining in FPGAs. So what happens here is that the first FPAA chip converts the input x into the output of x3, x cubed right here. And then the 2 gain hold blocks here are used to sort of avoid the phase mismatch problems. We have discussed matching phasing in lectures previously. And and also this the second FPAA block here does the calculations for the differential equations. Yeah, and so this is how the Fitzhugh-Nagamo block works. So what you should really note here is the use of a gain-hold block for coordination between the two uh, FEAAs. Next is I'm going to talk about neuron modeling in application-specific integrated circuits. So this is a step up in terms of difficulty. We first started with the FPGAs, which are sort of simple, and then we moved on to FPAAs, which were slightly more complicated in terms of implementations. And now we talk about neuron modeling in ASIC circuits, which is going to be significantly more difficult. So the four models that we are going to evaluate here are the Fitzhugh-Nagamo, the Cordic model, the Isaakovich model, the Hindmarsh-Rose model, and the Fitzhugh-Nagamo model. We've already talked about the Fitzhugh-Nagamo model previously. So I won't involve their equations here. So this is the Cordic equation, this is the Isaakovich equation, this is the Hindmarsh-Rose equation. And what is interesting here is that Isaakovich here, what's interesting about the Isaakovich neuron is that when Isaakovich was describing his neuron, he quite literally said that these models are supposed to be a reduced version of the Hodgkin-Huxley model. And we can actually quite see the quite reduced nature of the Isaakovich model because it only uses two ordinary differential equations, whereas the Hodgkin-Huxley, if you remember previously, used 4 differential equations. All these models are actually quite computationally simple compared to the Hodgkins and Huxley model. And that's sort of been the goal since after Hodgkin and Huxley model had been developed, because everyone felt that it was a little too complicated for implementation on FPGAs or implementation on hardware generally. Moving on to my next slide. So here, here in the ASIC implementations, the layouts for these ASIC models were made by using industrial hardware calibrated TSMC 130 nanometer CMOS technology. And the full width at half maximum error here mentioned here is actually used to compare these models with the Hodgkin-Huxley model. So the definition of sort of this value is that the width of the spikes of the different models at the halfway to the maximum is measured and compared to that of the Hodgkin and Huxley model. So here we take the difference in the spikes and at halfway potential and divide them by the Hodgkin-Huxley value, and we take the percentage. So Cordic is quite similar. Isaakovich is deviates quite a bit. It deviates by 71.14%. Hindmarsh-Rose also is as quite similar, down to like 3.51%. And the Fitzhugh-Nagamo is quite different to the Hodgkin and Huxley model. So all 4 of these models were actually implemented in ASIC, and there was a comparison drawn between each of these models. So if you look, the number of ordinary differential equations, ODE here stands for ordinary differential equations, used in the Cordic model is 2, Isaakovich uses 2, Hindmarsh-Rose uses 3, Fitzhugh-Nagamo uses 2. The order of the differential equations here also matters. Here where Cordic uses 4, Isaakovich uses 2, Hindmarsh-Rose uses 3, Fitzhugh-Nagamo uses 3. Isaakovich has the highest number of modes of the spiking of all spiking neural net. I mean, of all these neurons. Now, when we look at max frequency, Isaakovich performs best. So if we are implementing ASIC circuits and we do not worry about anything and we want the highest frequency possible, we would go with the Isaakovich model. But now if we have a constraint on the area, then we should go with the Hindmarsh-Rose model. Because Hindmarsh-Rose model actually has the lowest area consumption out of all of these when implemented on ASIC. and also has the lowest power consumption, which sort of makes sense. With smaller area, we would have a lower power consumption. Uh, we can we can also one of the better characteristics of Hindmarsh Rose is, as previously mentioned, it has only a 3% deviation from the Hodgkin and Huxley model, which means that to go from 3% to 1%, we would pretty much have to triple our power consumption with the Cortic model. We would have to almost, yeah, triple our area as well, and reduce our max frequency. So overall, the best model here right now seems like the Hindmarsh and Rose model. The Fitzhugh-Nagamo model is quite small as well, but it is not that accurate. It was 300% off. So Hindmarsh Rose is the clear winner here. But right when we approximate these models, you can see the serious reduction of the Fitzhugh-Nagamo model right here. So the Fitzhugh-Nagamo model, once we performed these approximations, went down by 84% in size. So it went down to uh, 25,600 micrometers in size, and its power consumption went down 86%, making it the most efficient in terms of power consumption. However, this did not really help with its still deviation from the Hodgkin and Huxley model. So if you want accurate, you would go with Hindmarsh and Rose. If you want something that saves a lot of power, you would go with the Fitzhugh and Nagamo model here. And if none of that's a concern, perhaps consider the Cortic and the Isakovich models, as they take in considerably more power and they are larger in size, but the Cortic model especially gives a lot more accurate representation when compared to the Hodgkin-Huxley model. Finally, so we discussed FPGAs with Macaulay-Pitts neurons. We discussed FPAAs, which are field programmable analog arrays. I may have not fully defined that definition with Hodgkin-Huxley neurons, as well as Fitzhugh-Nagamo. Then we discussed ASIC with 4 different neuron implementations, and we considered which one was best for an approximate form, for a non-approximation, and we have so if we have if we're still designing neurons, prototyping it, then we would use an FPGA approach, as FPGAs are great for prototyping and testing out different implementations. But if we want a something that's in high performance, something that's very specific, only used for single applications, we would pivot more towards an pivot more towards an ASIC, as an ASIC would be able to perform significantly better than an FPGA for its specific purposes. So one nice comparison I want to draw off here is that when we implement to the a Hodgkin-Huxley model on the FPAA, we discussed that its power consumption was 40 microwatts. Now, if the human brain has 100 billion neurons, if we scale that neuron up to the FPAA requirements, so if we have 100 billion neurons in FPAAs, then what we would actually end up having is 70 megawatts of power to power the brain. Whereas a human brain actually just takes roughly around about 60 watts to run. So we actually have the human brain is a million-fold more efficient in terms of power consumption when compared to the Hodgkin-Huxley neuron on the FPAA. What should also be noticed is that simple models run faster on FPGAs than they do on ASIC. In terms of when we talked about a very, very simple Macaulay-Pitts neuron on the FPGA, it ran around about 190 megahertz. Whereas when we talk about our ASIC implementations, the best were running at 50 megahertz. Given that our activation functions were a lot simpler, we were using steps and ramps, whereas these guys have a significantly more complicated model, significantly more difficult activation functions and weight requirements and all of that. And that's about it for my presentation. I really hope you guys enjoyed it, and please let me know if you guys have any questions. I've also added two more slides here towards the end for links. So here are my references. I had 10 different references throughout this whole presentation. Thank you for your time, everybody. I hope you enjoyed.